Good morning. Today we're going to cover fabrication materials. We won't complete our coverage of fabrication materials today, but should do that on Thursday. And also on Thursday we'll start talking a little bit about fabrication. And along with fabrication there is a homework assignment which is really a overview of shop safety and kind of a test on shop safety, something you have to complete before we do any work in the shop, which we will start scheduling next week. We're going to split you up into groups, probably about 4 groups, and we'll have you sign up next week for this training that'll take place when you get back from spring break. That week following spring break is, we have some oral presentations, and then we have some shop training. And one of the things that you'll be doing, obviously, hopefully in the shop, is using a number of different materials for actual fabrication. If you're doing some prototype building, not all of you will be doing that, but the majority of you will, or should be. I think if I've looked at your project scopes, they do contain that particular requirement. So we'll overview a lot of the common materials that we do use in engineering designs and talk a little bit about selection criteria. I'm not going to talk about establishing design properties for materials because I've already done that. That was, we talked a little bit about that on safety, talked about how we run tests, get an average strength, get a distribution of strength, and we actually use a combination of those two to come up with typically what we call the 5% or 1% exclusion value, and we call that our minimum capacity, and we basically establish design values on that minimum strength or whatever it might be. It could be a minimum life in terms of hours, something like that. And we throw some factors of safety at it, and that's how we come up with design values. Knowing what kind of materials should be used for a project is fundamentally important. I'd say one of the biggest problems that we have with young engineers is they're just not familiar with materials. And they tend to make things out of stuff. Materials that they're probably familiar with, and that might have something to do with your upbringing more than anything. I would say it probably has something to do with your upbringing. I see it in 160 where students will gravitate toward building things out of wood, everything out of wood. And if you look at do-it-yourselfers, go to a lot of YouTube videos and look at stuff that they manufacture. It's out of wood. The principal reason for that would be, I would say, not because they're necessarily unfamiliar with other materials, but perhaps because of their fabrication capabilities. And that's something we will discuss, like I say, starting next time. Hopefully, you can work with most materials available out there. At least, hopefully you can work with them in our lab. We don't have capabilities to work with every type of material, but a good share of those. I would say that you're not going to gain a lot of knowledge on material usage here at the university. You typically do that when you're working on your own or after you leave here and are employed somewhere, hopefully out there in the real world. So the question is as we approach this today is, what's the best material for our particular application? Understand that there's over 40,000 at least useful metallic materials and another 40,000 useful non-metallic materials. There's a lot more than that, but we don't necessarily use those in engineering design. I just had an example here of hemcrete. I've never held a piece of hemcrete, but it just, looking at stuff online, and this is a biocomposite. It's made from the inner woody core of hemp plant, and it's mixed with a lime-based binder, but there's some characteristics of the inner core of hemp that makes it very unique and gives it the capabilities that it has with respect to binding with this lime-based cement. What we're going to look at in the lecture today is just run through metals, some wood products, plastics, ceramics, and concrete products. Those are our major materials of use, and that'll cover probably about 99% of what you'd use in industry. First of all, we'll look at metals, and as it says here in the broad sense, it's a chemical element, compound, or alloy that is malleable and ductile, usually solid, and it has a characteristic luster, and it's really a very good conductor of heat and electricity. We're going to look at three different categories. We can look at it as a pure metal, and that means in its elemental form. It's in its elemental form, and we definitely know that we have elements of iron, we have elements of copper, aluminum, nickel, gold, silver, for example. We typically don't use much outside of probably copper and aluminum as a pure metal. In all cases, iron is typically an alloy. We're using some kind of an alloy of iron is what I'm saying. Don't use nickel, gold, or silver too frequently unless we're working with electronics. An alloy we get by combining a metal with, or a pure elemental metal with perhaps another metal. It doesn't have to be. It could be some other element that might not be classified as a metal, but it'll give the alloy some unique properties. And then we have what we call sintered metals. And by the way, when we talk about an alloy, we're talking about something that we get when we melt things together. So we are going to heat them up till they essentially behave as a liquid, and then we're going to cool them down, and as they're being cooled, they're going to form these particular alloying crystals. Sintered metals is a little bit different. I'm showing you that probably on the next slide, talk a little bit about it is, but we can take some of those elemental substances, for example, we do this frequently, we grind them up very, very finely, and then we mix different ones together in different blends, and we put them together and we, under pressure, force them together, and then we heat them. We don't heat them, though, to their melting point. We heat them until they essentially fuse together, and that fusing is called sintering. And basically what happens is you're going to get atoms from one particular element or molecule that's going to fuse or cross over to another particular element or molecule, and that's how you get some binding. It talks about sintering. A simple example of it would be how ice cubes can fuse together when they're brought in contact. So you got two separate particles, you bring them together in a glass of water and they'll fuse. This is typically what a process looks like. You'll start out with piles, essentially, as you see here, of different elements that have been ground into a powder. And then what you will do is mix them, press them together to form some shape, and then heat that up and fuse it together, bind those together. You can see the sintering process. And then you could do some additional machining on that particular element before it's put to use. This sintering process we'll talk about a little bit later when we talk about ceramics, but understand that your pottery, plates, things like that, bricks made of clay are manufactured in the same way. They are sintered. You bring particles together and you heat them to a high temperature, but not high enough to melt them. Let's look at metals, our pure metals and alloys, and specifically what kind of forms that they come in, because this is kind of the terminology that you're going to have down if you're going to go order something or you're looking for pricing. We bring stuff in as tubes or pipes, and you can see some of the shots there. They could certainly be rectangular, round. We have some hex shapes ones over here, and here are some hex shapes that have a round center to them. And then you have a round OD with a hex interior. So you can actually literally slide one of these inside one of those. Keep that in mind. That's a way typically that you can maybe transmit power, for example, but have two shafts that slide one inside the other. And you want something like that, but yet you want to spin this one and have that one turn. this is how you'd start using some of these different shapes. We have solid stock, which we call bars. And they can be, again, rectangular, square, round, hex, similar to the shapes we just saw. We have plates, sheets, and foils, and understand that terminology is very specific. Plates are things that typically have a thickness greater than 1/4 inch, and foils, things that are less than 6/1000 of an inch in thickness. And in between there, we have what we call sheets. So if I want something that's 1/8 of an inch thick, I'm calling up for sheet stock. Now, when you specify it, I don't have that, and maybe I should put it on here, but I don't have the thicknesses with respect to their gauge number. When we order steel and sheet stock, we order by gauge. I'll call up and say I want 16 gauge, I want 14 gauge, I want 12, 10, 7 gauge thick steel. And 7 gauge is very close to 3/16 of an inch. When we talk about 10 gauge, we're talking about something that's close to 1/8 of an inch. Get down to, 14 gauge is like 0.07 inches thick. And those are thicknesses that we commonly use down in the shop. And I just called up, I want, a sheet of 7 gauge. He's going to ask me typically if I get something in that thickness, 14 gauge, if I want a hot rolled or if I want a cold rolled sheet. And I'm going to get to that in a second. Now you can get this, most of the stuff that we'll get in plates or sheets, the standard size is actually a 4x8 sheet. It's very similar to what you would get if you ordered some of our wood panel products, a 4x8 sheet. They also stock 5x10 sheets, for example. That's not an unstandard size in steel. Some thicknesses, they may not have that stock, but our local supplier can typically get it within a couple days. With respect to projects, I'll just put this out there. We do get our steel from a place in the south side of town. They're the big steel supplier in town called Wiedenbeck. And a nice thing about them is they give us a special rate, the UW special rate, and they also deliver here at no charge. And that delivery is the day typically following the order. If you order in the morning, they'll have it here tomorrow morning. If you order in the afternoon, typically you may have to wait a whole nother day because they typically will have started loading the shipment for tomorrow early in the afternoon, and you may not be able to catch the shipment. But it's hugely advantageous for you. And I want to point that out because a lot of you may want to have a tendency to jump online, which is what you should do, by the way. Jump online and start looking for pricing. And people can sell you steel or small pieces of steel. You could order a certain size, but you typically will pay as much for that small piece of steel they're going to have shipped in some places you would pay for that large 4x8 sheet that we'll get from Wiedenbeck. And typically for your projects, we probably order the steel, give you the piece that you need or a small cut you need, and use the rest for other projects. So just keep that back in your mind there that we'll want to do that ordering typically for you. If you only need a small piece, we'll get a larger piece. If you want something that's in a thinner form, you don't want that 4x8 sheet, you can order stuff thinner, and there's different terminology. Instead of calling them plates, and sheets, the thick stuff is called flat, and strips for the thinner stuff. And you could get a flat essentially by, cutting a plate into thinner pieces, and strips the same thing. But I want to point out that these are actually manufactured like this. These aren't cut out of a thicker piece of plate. And what I should make clear here is that when we're in the shop and we start with a big piece and we cut it down to size, we use a big shears, just like a big paper cutter, cuts that plate, and we can cut it into thin pieces like that, but those pieces will have a very sharp edge on them. Very sheared, sharp edge. This stuff, when you order flat, it doesn't have a sharp edge like that. It actually has more of a rounder edge because it's actually rolled to that size. And having that sharp edge is not a problem in our lab, because when we're working, we will come in and we will take a grinder and we will take off that sharp edge. We want to do that because sharp edges are dangerous if you come in contact with a sharp metal edge. Also, paint doesn't adhere as well to that sharp corner. paint tends to pull away from sharp edges or points. So you want to round off that edge. That we can do in our lab, but it costs money, and it takes it in terms of time and also grinding wheels to do that. It's not a problem in our lab, but it is an issue in industry. If you're working out there making large equipment, you really can't afford that extra time that has to make an edge round and that extra equipment. So you would typically order stuff in flat. And flat typically comes in very standard sizes, 4, 5, 6 inches wide. But understand that typically Wiedenbeck, for example, is not going to stock a lot of different flat. You got all these different thicknesses and all these different widths. They're not going to stock that kind of stuff. So that's more going to be a special order for them. We have rods and wire, which are really smaller diameter stuff. When I talked about bar stock, you're talking about some of the larger stuff. As it gets down to size, we'll call it a rod. And when we get down to very thin size, it's a wire. And typically wire will come in very long lengths that can be rolled up, as you see here. Okay, hot rolled shapes. These are sections that are standard in terms of their size. We've got what we call our I sections. There's S stands for a standard I section. W is a wide flange I section. And then we got C sections. They're just abbreviated with a C, and angles with an L. Now, just point out this angle here, and we're going to show you how it's made in a second. But something like this, I don't know. I'm thinking if that's a 1/4 inch thick right there, this is maybe 2 inches by 2 inches. So that's, that's a 1/4 inch by 2 by 2 angle. The nice thing about angles, now we can make angles, and we do this a lot down in our shop. We make angles out of sheet and plates. We shear a strip out, and then we bend it, and we can make this same shape. But again, our shape is going to have, if we've sheared it out, it's going to have sharp edges on it right here. And when we bend it, we may not get it exactly 90 degrees. Again, it's not hard to get it close. But this thing is going to come perfectly 90 degrees, and it has those rounded edges on it. It's going to cost more. It's going to cost more for you to buy this than it would for us to make that angle out of a piece of flat sheet stock. These come like, different thicknesses. Like I mentioned, 1/4, 1/8 is very common, 3/16 is very common. It's common to get them a 1 by 1, 1 by 2, 2 by 2. Those are very common sized angles, and they would stock those at Wiedenbeck. When you start getting into C sections, they're pretty restricted in terms of what they would stock, because that's not a common order. You got a thickness to it, you got a width, you got a depth. Same thing with I sections. I sections come in a variety of sizes. We use I sections typically in high-rise steel construction. In low-rise steel construction, by the way, we don't typically use I sections. We actually make our I sections out of plate, flat sheet, flat stuff. And the reason is that for lower rise buildings, we typically want to have the perfect shape for the loads that we're seeing. And for people that are familiar with mechanics of materials, understand that the higher the bending moment, typically the more depth you want in your I-beam. And your bending moment changes as you go along the member, so you'd want your depth to change as you go along the member. Well, these things have a fixed depth, so it's not efficient to typically use those types of sections. You want to have something specially made. And for our lower rise steel frame buildings, that's what we do. We make our sections, we make I sections, but we make them out of, we weld 3 pieces together to do that. So let's look at actually hot rolling. We'll start with that. We talked about these hot rolled sections here. Let's look at how they're actually made. And it starts by actually casting a slab, what we call bloom or billet. We also have a special what we call beam blank. That's another shape that's cast, and here is a beam blank. This is what it looks like coming out of the furnace. You can see it's shaped. It's cast into this shape, and what we're going to do then is we're going to take this and we're going to actually roll it while it's hot into a series of shapes. Here you can see how an angle is actually made. A lot of people aren't aware of those hot rolled angles that they use, how they're actually formed. You actually start with a thin slab, small slab, and you can see some of the deformation that goes on, and it's kind of strange the way that it's done, but that's how you end up with your angle. These are all passes that go through a series of rollers back and forth, and you eventually work it into this shape. Here's your I-beam, which starts with a beam blank. You get this, and we also make sheet pilings, and I don't know if you are familiar with sheet pilings, but if you take one of these, if you can imagine you've got another one of it, you can take the other one and you can slide the next one. You can flip it around 180 degrees and you can slide one of these right down into the other one, and you get a series of those that are all connected. And we use those to hold back dirt. We can push these whole things down into the ground. Well, you know, you got one stuck in the ground, you slide the other one right down into the ground, and you can hold back soil with it. You can also hold back water. We make what we call cofferdams, temporary dams that we're holding back water as we work inside of those, that piled off area. We have cold finishing, which basically involves rolling these members again between rolls and trying to change their shape while they're cold, not while they're hot. So hot rolling, the billet is hot and it's easier to deform it. When you cold roll, you really are doing some things. You're kind of, as it says here, you're introducing defects into that crystalline structure. And that can actually increase its strength. There's this, what it's called Hall pitch hardening, and if you keep the more you keep cold working something, actually the higher its yield strength, the stronger it essentially gets. It's very much the case with wire. Wire, what they do to reduce the size of wire is to run it through basically just a small die that just makes it smaller. You stick it in there, you get it. Once you get it started, and you start pulling it through. This reducer, it'll make it thin, and they can do that very, very rapidly. It generates a tremendous amount of heat, by the way, in the equipment that's around it. But they'll do that multiple times to get wire from one size down to another size. And it'll go from a yield strength like down to 30,000 pounds per square inch up to like 150,000 pounds per square inch. You can really get some high yield strengths by continually cold working these metals. So it says most sheet steel has been cold finished, and you'll definitely see a difference down in the shop. I can show you when you get down there a thicker piece that's not cold finished and one that is. The cold finish stuff definitely has a shiny surface. Sometimes you look at it and you're thinking, well, I'm looking at a piece of stainless steel when you get it from Wiedenbeck. It's not. It's just a cold finished piece of low carbon, or it looks like a piece of aluminum. I mean, it can be that shiny, whereas you won't see that in a hot rolled surface. Understand, when you're hot rolling something, in those particular cases, you've taken something out of this furnace and it probably has a little bit more of that, you know, carbon surface on it, and that just basically stays there, and you got a darker surface and it's a little bit more pitted. It's not going to be near as smooth as your cold rolled finish. So that's just an introduction to steel. But you'll see a lot of all the components that we have. They're very standard components. We have them all down in the shop, and we use them a lot. And whether or not you use a hot rolled section, or you form your section, an angle or something out of flat stock, is, you know, it depends upon sometimes what you want to do. And I go both ways for different reasons, and you'll get an appreciation for that as you hopefully work on your project. The next area we want to look at is some wood products, and I've got 3 different categories here. I've got some samples of the second and third category, wood-based panel products and engineered lumber. You're probably most familiar with what we call solid sawn wood, where we just saw pieces out of a log, and then we will plane them off, sand them off, and that's what you get when you go to your retail lumber yard or big box store like Home Depot, Menards, Lowe's, whatever. And that's, you know, we're talking 2x4s, 2x6s, 2x4x6s, 6x6s, things like that. We basically have three categories of lumber, and if you're an engineer, and especially in wood design, you become very familiar with these sizes. Basically, and the rest of the public probably misuses all these terms as far as we're concerned as structural engineers. Boards are members that are nominally less than 2 inches thick, nominally less. So a 2x4 is not a board. And by the way, a 2x4 is actually less than 2 inches. I say nominally in name only. If you go and you ask for a 2x4 and you measure it, its size is going to be very close to 1.5 inches by 3.5. That's what we call an S4S 2x4, and don't worry about the S4S. It stands for surfaced on 4 sides, but although it is actually less than 2 inches, nominally it is supposedly 2 inches, so it falls under the category of dimension lumber. And anything that's 2 inches up to and including 5 inches is a piece of dimension lumber. We're talking about its narrowest dimension here. And if its narrow dimension is greater than 5 inches, then it's called a timber in, again, design jargon. So that's solid sawn lumber, and just understand, a 2x4, 2x6s, 2x8s aren't actually 2x4 inches. They're something less. So let's look at what we call panel products. And panel products are thin sheets of wood, and we make them in different ways, as you'll see here. The common size is 4x8. You can get 4x10, special order. Typically getting something wider than that is not common. There is some stuff that's specially manufactured, but it's not typically for sale. It is something that would be manufactured for use in some special product that a manufacturer is making, and they just want that wider size. Not something that you could special order retail. So let's look at these different panels, and I'll pass them around in sets actually, so you don't have to get up too often. First of all, we have what we call all veneer panel products, which we also call plywood. And what it is we're making it out of thin, what we call veneers. Those are thin layers of wood. And we get veneers by peeling them typically or slicing them. But the most common way is shown on the left, and that's rotary turning, where we are peeling it off a log. So you've got a log, you stick it in, it gets stuck in a lathe, and it gets spun around. And as it's being spun around, this knife edge is fed into it, and you peel off this thin layer of veneer. These methods over here of making thin layers of wood are only used for very special plywoods where you're interested in a particular appearance on the surface. 99.99% of the veneer is this. So I don't want to be misleading that one is just as commonly used as the other. Those other two are very, very infrequently utilized. This is kind of what it looks like as wood is being peeled off of a log. And you can see maybe a close-up shot of this cutting edge here. This happens very, very fast. If you're standing by this, you can't see, it's just a blur. You would never be able to pick out any of those knots. That's how fast this stuff comes off. You're talking hundreds of feet per minute. That's how fast this stuff goes. It doesn't, these logs, when they start running a knife in it, they just go like that. Next one gets dropped in, peeling starts. By the way, they typically run logs through a hot water bath, and they're in there for a couple hours. So this stuff is when it's peeled, it's got a fairly high moisture content. So basically, glue. What you do with that plywood, then, as you can see it there, it's being glued together. If I jump back, we glue it together in layers that are 90 degrees to each other, and the reason we do that is because wood is very weak in tension perpendicular to grain. So what do I mean by that? Well, you can see the wood grain. Here's wood grains running this direction, it's running this direction, it's running this direction. If you were to pull wood perpendicular to grain, this is the direction of the grain. If you run perpendicular to that, it's very easy to pull it apart. It's not easy to pull it apart parallel to grain. Also, it's easy to compress it perpendicular to grain as well. By alternating layers like that, we get fairly good strength in both directions, and it also enables us to actually like pound nails into it without splitting the panel. If you pound a nail in over here, just in this layer, it's going to split along the grain, and you're probably familiar with that if you've worked with wood and pounded into a 2x4. The grain's all running in the same direction, and you split it along the grain. Very hard to split a panel. Even if you nail right next to the edge, it's almost impossible to split it. Because if you nail close to the edge, you have to understand that like this one might want to split, but it can't because it's glued to this layer, which is holding it together, keeping it from splitting in that other direction. So that's the advantage and the reason why we alternate the layers. Then we have a series of panels that we make out of particles. And we got basically two main classes of particles. We got particle panels. We got what we call particle board, which is made out of very fine wood particles. I'll show you a slide. And then there's a class of wafer boards, but we don't make this anymore. We've went to what we call oriented strand board, which is really a special wafer board if you want to be perfectly honest about it. But here's particle board. You're familiar with it. It's a very dense product. It's just, you're taking byproducts of other operations and gluing them together. It has a pretty high resin content. But again, very uniform, very dense, and therefore it has some major uses. And then we have really oriented strand board. And what we're doing there is we take the log and we actually, we make it into lots of strands. So there's a special machine called a strander that does this. You just drop the log in there and very quickly spits out lots of strands. And they're fairly thin, maybe up to a foot long, inch wide. And what we do with those strands is we lay them down, we put adhesive on them and we drop them onto it's just a belt, a moving belt. But you drop them on there, so the first ones that go on are kind of generally orientated parallel to the belt. And that's very easy to do, actually, to orientate these strands. And then we put another series on them, and we kind of lay those the other way. We're actually trying to emulate plywood, is what we're trying to do, and we do this. The reason that we use strands, by the way, and the reason that we make this product is there's a couple reasons that we have it. Number one is in place of plywood. Number one is that plywood, to make plywood, you have to have complete veneers. Understand that when you first start peeling a log off, you don't get a full sheet like this. Logs are tapered. And you start running that knife edge and you're only hitting that log at a few spots. And you got to get in a little bit before you start getting a full sheet off of there. So all that first stuff is just garbage. It's thrown away. The other thing is you can only peel so far into the center. And we actually don't necessarily want the center of the wood either. That's what we call juvenile wood. It has very different properties. At least we don't want a veneer, just one veneer that's solid out of the center. So we don't use the center. That typically gets used for fence posts. That's what fence posts really are if you go to the store. They're the center of a log that's been typically peeled. The other thing is you got knots. You see all those knots in it there? And typically, sometimes they fall out during the operation, but that can lead to voids. Sometimes in those inner layers of your plywood, there's a void in there, and that can cause issues in material use. With stranding, all we do is remove the bark off the log and the rest of the log is used. The entire log gets strand. And although there's some juvenile wood, that center is there, we can still, that center stuff gets mixed in with the outside stuff. So you kind of got a uniform blend of all kinds of pieces. Knots will get busted up in that process. They'll fall out. And understand that once it goes through the strander and we strand this whole log up, we screen it so all that fine stuff like those knots would fall out and we're just left with these nice strands. So you get back to formation, you lay strands one way, you lay them the next way, you can lay another layer on this way and so forth. You alternate them. That's why it's called oriented strand board, because you're orientating those strands as you're putting this stuff together. And then you just press it all together. It's got adhesive, you press it together, heat, and you get your panel. And we'll pass those around in a second. This is just one of the things here. This has got a unique surface on it. The piece I'm sending around will not have that surface on it. The piece I'm sending around is not going to have a sanded surface. That's what you're looking at here. This is sanded, and this is not. The piece I'm sending around is going to be unsanded. You sand these things if you want to give them a very specific thickness, or you want a nice smooth surface on them because you're going to put something on them. Typically for flooring, we'll have a sanded surface. This one that's coming around also has a screen imprint on the back, and that's pretty common with stuff that gets pressed together. We're trying to, if there's heat involved, we maybe need to let off steam. There's water moisture in here. We might need to let some of that out. So you'll see that here, and you're going to see that on another product I'm going to pass around. So this is for a floor, and you can see it's a sanded panel here. They've got tongue and groove edges so they can fit together, and that's important for other reasons in construction. The third class, so we have all veneer panel products, then we have ones made from particles. Now we have ones made from fibers. And this is really a pulping operation. We start it the same way that we make papers, exact same process, okay, pulp it. So you got all these fibers. And then we put those fibers together fairly loosely. And the color that you get, this is cellulosic fiberboard. That's putting the fibers back together in a loose fashion. I'm going to pass some of that around. The color that you'll see here is the natural color, the real color of wood that's pulped. And same thing with paper. If you were really going to make paper and you didn't bleach it during that particular process, you'd end up with something that's this color. So your paper would be. So we can compress it to different levels. Here it's loose, we call it cellulosic fiberboard. We've got what we call medium density fiberboard, and we haven't applied too much pressure, but medium density fiberboard is something that gets used frequently in your knockdown furniture. That is really the center of most of your knockdown furniture. It's something that they can machine into really nice shapes, and then they can and get it nice and smooth, and then they can put on very, very thin pieces of wood. And I'm going to pass this piece around that you see up on the slide here. And then we go to the extreme. We press it as tight as we can, and we get what we call hardboard. Now, I'm showing you here pegboard. Pegboard is made from hardboard. I'm going to pass hardboard around without any holes in it, but if I put holes in it, that's pegboard. In this particular case, I'm smooth on both sides, but when we typically make this product, we have to, when we initially press it, we do have a screen on one side. It's a smooth plat on the other side, but it has to have a screen on this side to let out that steam during the pressing process. They'll come back and actually press in, put this back through a press to get both sides smooth. That's just an extra operation. If you're making pegboard, they don't go through that extra operation. So you always on pegboard typically see that screen print on the back of it. So that's just the manufacturing process. Here is laminated paperboard. So we actually make stuff like this where we just make it into paper first and then glue all the sheets together. Laminated paperboard. I forgot to bring a piece along with me. So I'm just going to pass these products around quick, and we'll see how long it takes to get through around class. But just examples, and I've written on them. So don't ask me how you're going to. I probably should have started it up there and brought it down the center. But if you get a chance to look at them, good. If not, you can look at them after class. We've got other special panel products. I won't talk about them specifically here, but they're on this slide. This is one of them, lumber core, which is just putting solid lumber in between a couple pieces of veneer. It's really a nice product to use for cabinetry, in my opinion. And now we've got the third thing we want to talk about, and that's engineered lumber. So one of the issues with 2x4s and 2x6s and so forth are that they have undesirable lumber characteristics in them. At least they're undesirable characteristics of growth that reduce the strength for our application, for structural applications. And one of those is, knots. Now, knot is a result of, a branch growing at that location on the tree. It's not a defect. A lot of people like to call knots defects. Well, they're not defects. That would be like saying you're defective because you look different than that person or something like that. I mean, it's bizarre. That's the way a tree grows, right? It has to have branches. And when we cut it out, we end up with a natural characteristic of a knot, but the way we cut it will reduce the strength of what we want to use that piece of wood for. So we try to basically compensate for those by spreading them out. So if you got a knot in a piece of wood, and I got a real weak spot at that thing, I can compensate for it by trying to spread them out. And how am I going to do that? Well, typically what we do is we glue together several layers. And that's what all this stuff is really about. It's by, instead of having one large knot running all the way through here, this is what we call glue laminated timber, glue lams. I've got 3 pieces glued together. Well, yeah, one might have a knot in it right here, one might have a knot in it over there, another one over here, but at least knots are spread out. So I don't have a weakness all the way through it at the same point. Just spreading it out. And that gives us, very uniform properties. By the way, sometimes one piece of wood is more flexible than another, and you glue them together and you get an averaging effect. So again, this is what's important is I talked about allowable design properties, right? Last time we talked about, if you have a rule-wide distribution, that can be a problem because the wider the distribution, the farther that left tail area, so you're looking at it my way, the left tail area is way over here, and that's what dictates your design values. It's the weakest one that dictates your design value. You want a nice tight distribution of strength so that you're utilizing all your material really well. I mean, I don't want to have a bin full of lumber where I have real weak ones and real strong ones, because when I grab it, I got to assume that I've grabbed a weak one. And all my design properties are based on the weak one, and I'm wasting all the strong lumber. So you want to make sure that when you have a selection there, that everything has about the same strength. And that's what we get when we start doing this. We get very uniform properties, which means we have higher design values and we can more efficiently and more effectively use our lumber. So this is just gluing pieces of wood together. That's what we call glue lam. This is laminated veneer lumber. So I'll pass a piece around. I don't think I had said anything on it, right on it, laminated veneer lumber. In this particular case, what we're doing is we're just taking those veneers again, and we are gluing those veneers together, but we are not orientating them 90 degrees to each other. And there's a reason that we don't do that, and that is because lumber, or wood, is only strong in that one direction. And when I'm using lumber as a beam, and that would be in your floor system or in your roof system, I want the grain to all run in that one direction. That's where it's being stressed. It's being pulled and pushed in a direction along the axis of the member. I do not want to take half that lumber and turn it this way, because it won't help me. The downside of this, you understand. You know what the advantage of going crossways was, is that you had strength in both directions. And also when you put a fastener into a piece of plywood or something where you've laid one layer this way, one layer that way, you don't get splits. This stuff, believe you me, you drive a fastener into it, it will split just like a piece of lumber will, because all the grains run in the same direction. But again, you have all these very thin layers, and if you did have a knot, and you saw that veneer, looked at all those knots on those veneers, when you glue them all together, those knots are all spread out. And you have how many different pieces of wood that might be represented in here in this veneer. And I'll hold on to this till I pass a couple other ones around. But again, it's just a really efficient product because it spreads out defects. The other thing that we do is some of those veneers, I talked about when you start peeling off wood veneers, you start running that thing into the log, and you're not getting out full sheets of veneer. You start getting off it starts throwing off some chunks. And some of those pieces are pretty long. And then you get some veneers that are just really, really bad because they have these huge knots in them and they don't want to use them for plywood. What they do is they take those veneers, those ones that aren't full, or there's one with big knots, and they clip them. They make them into thin strips. Some of those strips are long, some are short, doesn't make any difference. They then glue them all together and they get what we call parallel strand lumber. This is probably the most expensive lumber that we can get, and it tends to be some of the highest strength lumber we can get. So you can look at the end grain, I'll pass one around, but you look at the end grain here and you can see it's just all lots of thin strips of lumber. But these are veneers that couldn't be used for something else that got clipped up and glued together. It's ironic, okay, in that traditionally what they thought was garbage and that they did not use. They take those veneers that weren't good, they take them and they make them into a product that ends up being perhaps the best engineered product we have. At least it's the most expensive, but it has high strength values if you look at it. And you can actually take some of it and, like any kind of wood, you can make, you can put it on a lathe and turn it down. This just has a real neat characteristic when you do stuff with it, so I thought I'd just throw that slide on there. Then we have laminated strand lumber. Laminated strand lumber is just like oriented strand board. Those same strands that we make to make that oriented strand board, what if we orientate them all in the same direction? Again, it's just like we have plywood and then we have laminated veneer lumber. The plywood, we take the veneers and we orientate them 90 degrees. Laminated veneer lumber, we run them all in the same direction. Oriented strand board, we take those strands, we put them 90 degrees to each other, and then in LSL here, laminated strand lumber, we take all the strands and we run them in the same direction. We use this product, by the way, today is predominantly used for studs. Today, if you're making high walls and so forth, you don't want to use typical 2x4s, 2x6s, because what will happen is that stuff, it'll crook, it'll twist, it'll do all kinds of strange things on you. This stuff dimensionally is very stable, and if it's going to expand in size a little bit, it's going to be fairly uniform and expand in size or shrink in size only as it absorbs and desorbs moisture. It's not going to do any of this bowing and twisting and crooking and cupping that you typically would see with other lumber. So it also is very uniform, so it has higher strength properties. We use a lot of, believe you me, we use a lot of engineered lumber products today. Here's actually, I passed this around a little piece here. These are I-joists. The most efficient section for a beam, if you're putting a lot of load on the edge of a member, you want an I shape because all the load is taken by the top and the bottom, so that's where you want to put your material. In this particular case, what we do now, and you're probably familiar with this if you live in a newer house, you've probably got wood I-joists. They got laminated veneer lumber up on the top. They've got an OSB web member typically. It's got a little bit higher resin content than most OSB, but that's what you're getting. So, almost exclusively today used for floor supports. This is just, was a job site. This is the house right behind my house, and they just built that one a couple years ago. And interesting, they've got a wall that's being framed out and it's laying on the deck, on the floor as it's being constructed. But interesting that I've got OSB, I had parallel strand lumber and laminated strand lumber all showing up on that job site. That whole thing is being framed, that whole house being framed out of engineered lumber products. No solid sawn lumber in it. And that's high-end construction today. Okay, we'll look at some plastics. And I'm not an expert in plastics, but we've got some slides here to show you some different types of plastic and what they're used for, and you'll get an idea that things are really, really broad. And we're just talking about a group of synthetic and natural organic materials that typically can be shaped when they're soft and then hardened. We've got two main categories, thermoplastics and thermosetting ones. Thermoplastics will not undergo a chemical change when they're heated and remolded, so that can be done again and again. And you're going to see that the thermosets are the ones thermoplastics are the ones that you recycle. They're the ones that will have a special number. We're going to look at those numbers after we go through a few of these. Thermosets are a little bit different. You can melt them, they take shape once, and that's basically it. And there's not much you can do with them. Recycling is not an option with those unless you're going to reuse that material in the same shape that you had it before. And I mean, we can do that. We can take tires, right? We've taken tires and cut them up and into different shapes and maybe bolted those pieces together. I've used them for, absorption, vibration. There's different applications for those materials, so just don't think I should be a little careful or saying that we can't reuse them. You just can't reshape them. You got to cut that material up as it was originally provided to you. So we got polyesters, and I've got the abbreviation for them there as well. You can see fibers, textiles. We've got polyethylene terephthalate or PET, and that's typically what we're using for our water bottles. Polyethylene, you're very familiar with. We use a lot of polyethylene sheeting, very thin film. I use a lot of it in construction for vapor retarders. We use it for, curing purposes. You obviously see a lot of bags with it. Your big noodles, by the way, are polyethylene. High density polyethylene, something that we use a lot in the food industry. We talked about different different materials last time for food safety, or the time before, whatever. But understand that there are plastics that can be used. High density polyethylene almost always will meet food grade requirements. A lot of good structural applications there. Polyvinyl chloride, you're familiar with, PVC for short. We got PVC clad windows. You can see all the different fittings and piping here. In some cases, be careful. There's different additives that will make it more resistant to UV radiation. Those are obviously certainly used in window cladding applications for PVC. Not so often in piping. You typically do not want to expose PVC piping to sunlight because it will typically break down. We got low density polyethylene, just a couple examples of those. And we got polypropylene and fibers. We typically, you can use the ropes that we typically have will frequently be polypropylene. We actually take thin fibers, and if you've, some of you that might be in construction are familiar with fiber being added to concrete. I'm not a fan of that. I don't think it serves any major purpose. It just drives up your costs. But those fibers would be polypropylene fibers in most cases. Some of the special boards that we're using, and this we use a lot actually in housing, animal housing specifically for pens, to separate pens. You've seen this board. Those are typically polypropylene boards. Polystyrene, you probably know it as styrofoam. It was developed by Dow Chemical, and their trade name for it was styrofoam. But it can come in a couple different forms, either an extruded polystyrene, or we have what we call expanded polystyrene. Expanded polystyrene, we typically call the beadboard stuff. If you look at those coffee cups that look like they're made out of lots of little small beads pressed together, again, that's polystyrene. Only beads that were actually pushed and put into a form with the addition of steam. So they're put in there in a pretty warm state, and they consolidate and bond together. We got polyamides, or nylons for short, and you're familiar with a lot of brushes, your toothbrush, nylon tubing, nylon rope. And then we got acrylonitrile butadiene styrene, I guess is how it's pronounced, ABS. Acrylonitrile butadiene styrene. Yeah, I think that's right. Electronic equipment cases. Obviously, probably a lot of you are familiar with instrument cases. We've made, when I was working for Gale Company, we made our gas tanks out of ABS. They were rotomolded. So what you do is you basically have an outside mold. It's like a clamshell, basically, you bring together, and then you introduce the material into it, and this whole mold is rotated and spun on a couple different axes so that the plastic is forced to the outside of the mold and gives it a uniform thickness, and then you just take the mold off and you have your tank. Those were ABS tanks, and those are how they were manufactured. Polycarbonate's a higher impact resistant plastic. This is very commonly used in our industry. It's a little bit more pricey. There is some fiber reinforced plastic, fiberglass types of skylights that you can use. If you want to pay double and have a good product, you would probably purchase this polycarbonate instead. We use a lot of this on greenhouses, this form of polycarbonate. Again, because it is translucent or fairly transparent more than being translucent, but it lets a lot of light through. Polyurethanes come in a lot of different forms depending upon their density, and a lot of people don't realize that. You can get some dense forms of polyurethane, and then we actually have some foams. And what we're doing is we're taking that same plastic, but we put in what we call blowing agents in it. And those are typically liquids that are mixed in with the plastic. And that's done under pressure. And then when you release the pressure, the blowing agent is something that goes from a liquid to a gas phase when that pressure is reduced. You know, a lot of things, everything basically out there can go from a gas phase to a liquid phase via a change in pressure. So, meaning that if I take a gas and I compress it enough, it'll become a liquid. Okay, and then if I release that pressure, it goes back to being a gas. Same thing that's blowing agents. Blowing agents do that at like room temperature. They should be in the gas phase, but under a little bit of pressure at room temperature, they would be in a liquid phase. Your refrigerants, that's what your refrigerants do, right? That's what makes them the special materials that they are, is their ability to go from that gas to that liquid phase when they are under pressure and then go to atmospheric pressure under normal temperatures, room temperatures. We use a lot of polyurethane foams for building insulation as well. So we use polystyrene, but we also use urethanes. The stuff that we spray on, that's usually a urethane. Melamine formaldehyde, the biggest use of that is for surfaces on your desk? Yeah, so your desk have that surface on them. You have a melamine formaldehyde surface on the desk that's sitting in front of you. What you have is it's put over, that's actually a paper overlay put on material that's probably a particle board table with paper over the top and then melamine formaldehyde finish on it. Phenolformaldehydes, we use those again. It's used very much like, I'll back up here. Used a lot like our melamine formaldehydes, and it's also like some of the other phenolics that we're going to look at, some resins for bonding. You got polymethyl methylcrylate, PMMA. Your hard contact lenses are made out of that. More importantly, plexiglass is a trade name for PMMA. And you can buy plexiglass routinely at any big box store in a lot of different thicknesses. Polytetrafluoroethylene, PTFE, which is Teflon. And we got Teflon tapes, Teflon coatings. Urea formaldehyde, again, another one of the phenolics, just like melamine formaldehyde. And this urea formaldehyde is really the adhesive that we typically use for exterior applications of lumber. Now, also interior applications. Basically, all those engineered lumber products have this as an adhesive. So they can be used outside, inside. And then some of the code for those thermoplastics, the ones that can be recycled, just showing you some of the standard designations for those. Number two is, like I said, the one that you typically can use for food grade uses, and that's your high density polyethylene. Your low density polyethylene is number 4, polypropylene, polystyrenes, other types of plastics. So all the ones that we kind of covered already, all listed down there on the bottom, and now hopefully those numbers mean a little bit more to you. The next category of materials is ceramics, and those are inorganic, not organic, inorganic, in this particular case, non-metallic solids formed by the action of heat. And what we're typically doing again is taking really soil minerals, typically clay minerals in this respect, and packing them together just like we did with our other sintered products, forming them into some kind of a shape and heating them up. Now the process is typically a little bit different than what we'd use for sintering, basically because when we start with our clay bodies in this case, and that's what we call those clay minerals that have some moisture that we formed, okay, that's the stuff that we're going to form into our finished product. We're going to call that a clay body. And if it hasn't yet been heated, it's called a green body. Now, the heating process, okay, which again, most of you have probably called firing up until this point. You're going to fire that pot. That's also called sintering. We talked about sintering before. That's what it is. This has a little bit more detail on sintering. Just talks about the 6 different distinct mechanisms that are involved in what we call solid state sintering. Solid state sintering, by the way, is all the sintering that takes place before anything starts to melt. So you have different minerals in there, and some of those ingredients will at some point melt. And not all of them will melt. And that's sometimes advantageous, because when some melting occurs, it actually fills in some of the pores between the other particles. And depending upon how much melting you get and how much of those pores get filled, sometimes we've got what we call a vitrified piece of clay, vitrified clay, for example. Now understand that vitrified refers to liquid sintering. So that's another term for liquid sintering. When things start to melt, liquid sintering is called vitrification. So that takes place, and you get a more glassy finish and one that's non-porous. Now, in most clays, what we'll typically do is we just do a solid state sintering, and we get this really hard pot. And then what we do is we come back and we put a glaze on the pot. And that glaze has a lower melting point. And we can get lower melting points by putting additives into the clay, such as lime. Okay? And that lowers, so we got like called soda lime glass, by the way. Glass is made the same way in that we mix ingredients up and we heat it. But in the case of glass, what? We make everything melt. But we want to keep the melting point low, so we add different substances to it to drop the melting point down. Well, you do that with some of the stuff that you want to put on the outside of your pots as well. You have these different slips, and they have a lower melting point, so that when you put them on and you refire that pot again, the pot doesn't melt. Understand, if the pot melted, it would just collapse inside your kiln. It lose all its shape, its structure. You don't want that. You want it to keep its shape, but yet you want an exterior that is fairly impermeable. So just some materials that we, ceramic materials that we make, things that we make by heating up minerals. First of all, if our mineral is typically a silicate, pure silicate, we're going to get glass. Now we do add, like I say, some ingredients to that to bring down the melting point. And then the other one that we would have that we make out of minerals is cement. Portland cement is made the same way, except that when we're done sintering, we take that product, that mixture of all those minerals that are put in and sintered together, we take it and then we grind it up into a fine powder. And that's what Portland cement is. We'll show you that here. So just some of the things that are made, ceramics that are certainly used in our industry are brick, and you can see different applications of brick, clay flue liners, chimney caps, roof tile. These are all construction applications, floor tile, and then glass. So glass is, what we're doing here is we're heating that material up, the silicates up to the point where they completely melt, and then we're going to cool it down. And this is just showing a shot of glass production. How many have seen glass, been in a float glass plant? Anybody here? We've got 2 in the state of Wisconsin, one at Portage and the other one in Menominee. So the one in Menominee, well, both of them you can see from the road if you're traveling on the interstate, if you're on 94. So I take that back. Portage is not on the interstate. As you're traveling up, is it what, 39? It's right, it'll be right on the left side of the interstate. If you know the building, this big building, you can see it. You got to actually look back around your shoulder because of some trees that are along the highway there. But big facility. The one in Menominee is going to be on the right side of the road, right as you're starting to come into town, as you're heading toward the Twin Cities. You're going to see a long building along the interstate, and that is a float glass plant. And that would be Cardinal's float glass plant. And we know Cardinal makes a lot of glass and glass units. They have an operation in Spring Green. They have an operation in Toma where they utilize that glass. So that glass that's made up in Menominee is getting shipped around. The sand that goes into the glass in Menominee is actually mined right across the street, just about 2 miles away from where the plant is. So, and it's not that big of a pit, but they've cranked out a lot of glass. So, glass is just an amazing product when you think about it. The fact that you can look through it, it's got this solid, and it's corrosion resistant. It doesn't break down under light and radiation. Just an incredible material and an incredible discovery. The way it's manufactured, a lot of people aren't familiar with at least how we manufacture today, which is different than we did turn of the 18th, 19th century. This is a process that was developed in the late 50s and used in the 60s, and it's what we do is we actually we make molten glass, but then we extrude it essentially, as you see here, out onto a vat of molten tin. And the advantage here of using molten tin is it's a very heavy material, it's a metal, and the surface stays really flat and the surface is extremely smooth. And it does not react with the glass. It's like oil on water, same thing. They kind of repulse each other. So glass, as you extrude it on there, you put it on there and that molten glass will spread itself out onto that very flat layer of tin. And we can also pull that glass right over then the surface of the tin as it starts to cool. So this is a very long line, several hundred feet long. And even this section here is fairly long as well. It's not that short. I'm thinking that this molten tin bath is probably maybe 100 feet long. It comes out of there and it gets drawn over across an area where it's slowly going to be cooled. And then you got inspection, it's getting cut. There's glass they'll break as it's getting cut, or as it's cooling down, there'll be fractures in it, and that glass just gets dumped and remelted in this process. They control actually the thickness of it by how fast they're moving it, and they also have basically the wheels that just sit on the edges of this glass. It's a wide sheet, and kind of pull it out and hold it out as it's going down that line. Those are great tours. Something to do before you leave this earth is to at least tour a float glass plant. I think it's kind of cool to see glass being manufactured. And then we talked about cements, and we call these our hydraulic cements. Basically what we're going to do is take different minerals that give us a certain percentage of lime and iron and silica and alumina. And it depends on where you are in the United States or in the rest of the world, what actual resources you're using to come up with this combination of minerals. And you heat them all together, and they will sinter, and then you're going to grind it and pulverize it, and typically add gypsum to it to stabilize it so it doesn't set up in the bag. Basically what you're doing during this whole process is you're taking away the water, and it wants its water back, and you give it its water back when you're making concrete. The one thing I was going to say about clay, when you're working with clay, again, to make pots and so forth, one thing you realize is that you want to mold that. It has to have a fairly high moisture content for you to shape it like you want to shape it. And you need to let that water actually kind of evaporate off a little bit. And even you're probably familiar with this if you made pots, you'll stick it in the kiln, but you only heat it up at a very low temperature or in a drying oven to try to drive off some of that moisture. And the thing is going to shrink as you do that. As you drive off moisture, clay is going to shrink, just like soil. Soil with a lot of clay in it, when that soil dries out, you get cracks as the minerals are attracted to each other. There's actually, to a certain extent, a little degree of sintering going on there, where individual clay plates get drawn to each other. If you don't do that and you try to put it in a kiln and heat it up right away, you'll just blow your pot apart. All that water and air turn to steam and just blow stuff apart. So you need to slowly let that water try to vaporize and move out of that mass. And you're also driving off other things, carbon dioxide and some other things that will oxidize at that lower temperature prior to sintering. This just shows kind of a shot of a batching plant for ceramic materials. Just a few things about ceramics. They tend to be very brittle, very high in energy consumption to make them. We're using a lot of energy, and there's off-gassing typically associated with that kind of production. Not an issue in this country because we do have a lot of strict requirements for anything that's being generated and let into the air. Not so much the case in other countries. And with concrete, we've got a lot of different products. We're going to just close by showing different things that we make with concrete. We've got plain concrete, which is non-reinforced concrete, or we've got reinforced concrete, which means we're just putting steel reinforcing in it, and the steel kind of handles all the tensile forces. Concrete's very weak in tension. It's only got about 1/10 of the strength and tension that it has in compression. So we rely on steel to take tensile loads. And we've got a lot of precast concrete components, and we got cast in place concrete, where the difference being is that, cast in place means we're making the concrete or casting it right where it's going to stay for the rest of its life. Precast, we're making something at a particular spot and then moving it around. And, we make blocks, concrete blocks. This is just showing how concrete blocks are manufactured. This is some slides I showed in my residential class yesterday. I was just pointing out, not in this country, buddy. Going to be allowed in the plant. Different shapes used for different things. We're not going to cover them, just showing them on a typical job site, several different blocks. Half high, half blocks, half high blocks. Glazed concrete block, what we do here is we go right back to that sintering operation, that glazing. It's the exact same thing. You can take concrete and then put a glazing on it and go back and fire it, run it back through a kiln and put a surface on it, just like you would do with a pot. And it's not uncommon to see concrete block with glazings used in probably buildings like this. They tend to be a little bit more expensive, so we don't use them like we used to. But I know in these buildings here, biochemistry didn't spare any expense, so you got usually some pretty high-end finishes around here. Architectural stone, kind of a cheap alternative to real stone. Just showing you some of the stuff that you'll see put on buildings. It's just, you just have a plastic mold, and you put concrete in it. But before you put the concrete in, you put in some coloring. And that coloring that is just going to be surface coloring on that component. This is the back side of it, just regular concrete. And if you break them in half, you'll probably see something like this. But you can get all kinds of different appearances using those. This is a Nova brick, which is this is actually a concrete product that is just kind of stacked dry. And this is how it goes on. So something, if you're interested in a very simple finish to put on a building that does have some really good durability, and you're not a mason, can't lay up block or brick, this just hangs right off the wall of your facility. It's not uncommon. We use a lot actually in some post-frame buildings, agricultural buildings where they just want to spruce up the front of a parlor or something. Do something like that. And then you got pavers, concrete pavers, and concrete tile, just like we would have clay tile and roof tile and floor tile, we can have concrete. Granger Hall, perfect example, concrete tile on Granger Hall. That's some of the later stuff. So I'll end it right there, and I'll talk a little bit about material selection next time. We're going to talk about fabrication, get into fabrication. Make sure you hand in your homework. I didn't put on the Dropbox. I keep forgetting to do that, but this in the past, because everything was handed hard copy in the past, but I don't have a problem with electronic copies. So I put up the Dropbox this morning after getting an email from one of the students. I did grade your other homework, and I apologize for not bringing it. I was going to grab it, and I forgot to enter the grades, record the grades. So I will do that right away here today and bring that homework. That's the project scheduling homework. Bring that along with me on Thursday morning. I can't think of anything else right now. Thursday is also, when's the date for the, Thursday's the date for the written report proposal. Is that correct? So that's probably a Dropbox thing and maybe a hard copy thing. I better check and make sure I got some Dropboxes. I think there are Dropboxes for that already. So yeah. Any questions on that stuff, by the way? If you do, you should probably talk to your advisor. I did talk to some of my students on Sunday because one of my students did ask a couple questions which I thought were really important. And so, yeah, if you have questions, see me.
Do we alternate one, or does the group have one the same?
No. So this is an individual written report. None of them would be the same. Everybody has their own. The only thing that would be the same on your, remember, the only thing that's the same is your goal statement. You're all writing your own introduction. That's the big thing that's new in this report. The rest of it's pretty much what you've already handed in. You've handed in the goal statement, you've handed in specs, and you have handed in references, annotated references. You're pulling all that stuff together and then basically adding that statement of need or introduction on the front end. I think it also probably asks for maybe an approach and a schedule. Those are very similar things. No, I don't want any solutions. No solutions. That's not part. This is a project proposal. This isn't solutions. So none of that. And that shouldn't show up in your oral presentation either. Not to say you shouldn't be working on ideas at this point, but they shouldn't be showing up in any report.
Hi, Professor. So I was a little curious about our